Hello all, we will continue for the rotating magnetic field. We have three magnetic fields for phase A, phi maximum sine theta. Phase B shifted by 120 degrees, phi maximum sine theta minus 120. And for phase C, phi maximum sine theta plus 120. We will take a different instance of time or thetas, theta equals 0. We substitute by theta equals 0 in the equations for phi A and phi B and phi C. For phi A, sine 0 equals 0, then phi A equals 0. And for sine or phi B equals phi maximum sine negative theta or negative 120 at theta equals 0, which is equal to root 3 over 2 phi maximum. And for phase C, phi maximum sine 120, which is equal to root 3 over 2 phi maximum. We have only fluxes of phase A, phase B, and phase C. Then we can get the net flux, which is equal to 3 over 2 phi maximum, and its direction is between phases B and C. Here we have the flux from phase B, and here is the flux from phase C. Then the resultant is between them in the direction shown in figure. For theta equals 60, then phase A, phi maximum sine 60 equals root 3 over 2 phi maximum. And for phase B, phi maximum sine 60 minus 120 sine negative 60 equals negative 3 root 3 over 2 phi maximum. And for phase C, phi maximum sine 60 plus 120 equals sine 180, which is equal to 0. Then phase C, flux equals to 0. We have phase B, flux from in this direction, and for phase A, which is in this direction, we have the resultant between them as shown in figure. If we take theta equals 120, then we have phi A equals phi maximum sine 120, which is equal to root 3 over 2 phi maximum. And for phase B, phi maximum sine 120 minus 120, which is sine 0 equals 0, then phi B equals 0. And for phi C, phi maximum sine 120 plus 120, which is equal to sine 240, which is equal to negative root 3 over 2 phi maximum. This is for phi C. We have now the resultant flux, which is equal to 3 over 2 phi maximum, same magnitude, and the direction of the flux. We have flux from phase A and the flux from phase C, negative, and the resultant is between them. This is the direction of the resultant flux. Now we will see at theta equal 120. We have phi A equals 0, phi B equals root 3 over 2 phi maximum, phi C equals negative root 3 over 2 phi maximum. We have the flux from A equals 0. This is the flux from B, and this is the flux from C, and the resultant is between them, the resultant flux, which is equal to 3 over 2 phi maximum. At theta equals 240, we have phi A equals negative root 3 over 2 phi maximum, phi B equals root 3 over 2 phi maximum, and phi C equals 0. The resultant or net flux is equal to the net flux we have obtained from the previous cases, which is same magnitude, which is equal to 3 over 2 phi maximum, and the resultant flux will be between phases B and A. I'm sorry, this is for phase A, and this is for phase B. We have the resultant flux between them in this direction. At theta equals 300, we get phi A equals negative root 3 over 2 phi maximum, phi B equals 0, and for phi C equals root 3 over 2 phi maximum. Then we have phi net is equal to 3 over 2 phi maximum, and the direction is between phases C and A, This is the direction of the flux of phase A, and this is for the flux of phase C, and the resultant is between them in this direction. Now, from these figures, we can conclude that flux has a constant magnitude, which is equal to 3 over 2 phi maximum. This is the phi net, and is rotating in direction first C and B phases are operating, CC dash B dash B, then A dash B dash B, then A dash and C dash C, then B dash and C dash C, then B dash and A dash B, then C dash and A dash B, then C dash and B dash B. We can see from these 7 steps that the flux is rotating in every instant in space, but with a constant magnitude. What will happen if we swap any 2 phases of a stator winding? This will cause the rotation to be reversed, or the direction of rotation to be reversed. We have phase sequence A, B, C. This is the same as B, C, A. We begin by B, then C, then A. The same as C, A, B. If we swap phase A, B, and C as in the left side, we will obtain a direction of rotation in the opposite direction. This is A, B, C. If we have B, A, we substituted A with B and B with A. We swapped B with A. Then we have the rotation direction as shown in the opposite to the phase sequence ABC. And for ACB, it's the same as the previous one, and for CBA, the same as the previous one, as the direction of rotation is the same as we have the same phase sequence. Now we will see the principle of operation of three-phase induction machine. When the stator winding of three-phase induction machine is connected to a DC, a three-phase supply power source, three-phase currents are drawn. We have three-phase source connected to the three-phase winding. We will have three-phase currents drawn. Three-phase currents produce magnetic flux in the air gap that is equal magnitude or constant magnitude, and revolve around the periphery of the rotor by a synchronous speed, which is ns. The revolving flux causes EMF in the rotor based on Faraday's law, like the transformer action, but the rotor windings or bars are short-circuited. That results in flow of rotor current. Then rotor current will flow due to the rotor circuit is closed using the short circuits or the short end rings at the terminals of the bars. The rotor current interacts with the stator flux, producing torque. The rotor rotates in the direction of the rotating flux by a speed which is lower than the synchronous speed and is called N motor. Now we have another term which is called the slip S. F is the frequency of the current in the stator, and P is the number of poles, Ns the synchronous speed of the revolving magnetic field in the air gap. Ns is equal to 120 times the frequency over the number of poles in revolution per minute. And for the rotating speed in radians per second, we multiply Ns by 2 pi divided by 60, or we have 4 pi f divided number of poles, which is in radians per second. The difference between the rotor speed and the synchronous speed of the rotating field is called the slip, or the difference in speed between the rotor and the field. We have slip equals Ns minus N motor, or N rotor divided by Ns, as a percentage of the synchronous speed, where Ns is always bigger than the rotor speed. If the rotor runs at a synchronous speed, which is the case for no load, approximately NR equals the synchronous speed, then the at no load S equals 0, as difference is equal to 0. If the rotor is stationary and the rotor is not rotating, Nm or N rotor equals 0, the standstill or blocked rotor slip is equal to 1 at Nr equals 0. Now we will see a very important question. This question is, why can't the rotor rotate at the synchronous speed? Or why is the rotor speed less than the synchronous speed? As the rotor coils in this case will appear stationary with respect to the revolving field, and there would be no induced EMF in them. The absence of induced EMF in the rotor coils, there would be no current in the rotor conductors, and consequently no force would be experienced by them. No force will be experienced on these conductors. Since the rotor rotates at a speed lower than the synchronous speed of the revolving field, an induction motor is called an asynchronous motor, as N motor or N rotor is smaller than Ns and is not equal to the speed of the magnetic field. Now we have another term, which is the rotor frequency. When the rotor moves at rotor speed Nr, the stator flux will circulate the rotor conductors at a speed which is difference between the synchronous speed or the field speed and the rotor speed per second. Hence, the frequency of the rotor Fr is written as S times the frequency of the current in the stator, where F is the frequency of the voltages and currents in the stator windings. Now we will see the first example. We have a three-phase 20 horsepower, which is the power output, PO. This is the output power. 208 volt, which is V line. 60 hertz, which is the frequency of the stator. 6 poles, P equals 6. Y connected, induction motor connected in Y, delivers 15 kilowatt at a slip of 5%. Find first the synchronous speed. Ns equals 120 times the frequency over number of poles. 120 times the frequency, which is equal to 60. 120 times 60 divided by number of poles, which is equal to 6. We have synchronous speed equals 1200 RPM. The rotor speed, which is equal to Nr, which is equal to 1 minus SNS. 1 minus 5% or 0.05 times the Ns, which is 1200. Then the rotor speed is equal to 1140 RPM. The frequency of the rotor current, Fr, which is Fs times the frequency of the stator, 0.05 times the frequency of the stator, which is 60, then it is really equal to 3 Hertz.